Okay, how's it going, guys? I'm going to go through the last lesson of the unit again, and then I'll try going through the test review as well. So we're back on page, I don't know, but the one that where the top says finding a parameterization for a curve. So curve is a bit of a misnomer. A curve just literally means it means the graph of any function or relation. Literally just anything is a curve, including a line, which is what we find ourselves looking at right now. There's a point A at -1, 3, and then there's a point B at 3, -2. And so you're supposed to be writing a parameterization for the line that passes through those 2 points. And I said in class that the way I like to do this is not to write parametric equations right away, but to write a vector equation right away instead. Because we said that a vector equation for a line will always take the form of some vector xy. Now the vector xy really just represents any point xy, like maybe this point right here is the point xy. But we're kind of thinking of every single point as just being the terminal point of some some vector. So we're basically modeling every single vector that has its terminal point on this line somewhere. And so the way you do that is you kind of just pick point A or B, it doesn't really matter, because point A would serve as a vector that puts us up onto the line originally, or B could do that too. B could be some vector that puts us on the line. But the whole point of that first point that we choose is just to be the terminal point on a vector that puts us on the line. So I'm going to call that some point P1, P2, and I'm going to mark down that that can literally be any point on the line. So, it makes sense to choose A, it makes sense to choose B, but if somehow you could figure out the coordinates of some third point on this line, that would be fine to put there too, doesn't matter. Then what we do is we add on. Okay, now basically before I even do anything, my vector is now defined to be that vector A. So what happens is I start from the origin and then vector A shoots me up. I'm now on the line, so that's good. But now I want every other point that's on this line. So what I need is some other vector that directs me along this line. And of course, what better choice than the vector that just goes from A to the other point I know on the line, A to B. So that vector is called a direction vector. When we were talking about vector valued functions in the last lesson, that vector was called the velocity vector, but I'm just going to call it v1, v2. And then what we're going to do is add multiples of that vector. So if I add this vector once, then that'll map me from A to B. But if I add this vector twice, then that maps me from A to B by one vector. But then it's like you're adding a second vector AB. You'd end up at some point that's twice as far away from A as B is. If you look at the purple point that I chose at random, that might be at a t value of like 1.5. It's one vector away from A and then another half of a vector. If you wanted to get the points on the other side of A, you're going to let t, I didn't mention this yet, but you have to multiply this vector by t, because we're going to add all the different multiples of vector AB. And so one vector pushes me to B. 1.5 vectors would push me onto this random purple point. If I wanted to go backwards, I'd let t be negative. If it was -1, then I'd go one vector AB to the left of A, blah, blah, blah. But in that way, this equation will model every single point on this line. So that's it. I have parameterized the line now, because once I have these, once I have this, I almost want to say these, because I'm thinking about these parametric equations follow really easily from this vector equation. You just take the x, the x, the x, and you plug it all in. So I'm realizing now I haven't actually written the vector equation yet. I just gave you the generic rule. And I guess I haven't defined v1 and v2 super well. So again, P1, P2 is any point on the line. V1, V2 is any vector parallel to the line is technically what it is. So if it's any vector parallel to the line, then obviously given a point A and B, you'd probably just want to go with vector AB. But sometimes we like to use a unit vector. Sometimes we use something else. Who cares? But for our intents and purposes, I'm going to let point P just be point A for us. Then I'm going to let this direction vector be the vector AB. And I'm probably going to do that 99 times out of 100, and that's going to work out great. So that would mean then that my vector equation for this specific problem would be the vector equation xy equals the vector -1, 3 plus the vector. Now remember AB, we just do terminal minus initial, right? So vector AB, this color is not great. Maybe it doesn't stand out. I'll change it. Why not? How's about a nice, well, that changed everything. How's about a nice royal blue? Boop. Alright. So where was I going with this? The vector AB, you just do terminal minus initial. You do B minus A and B, oh god. B minus A, B minus A. So the vector AB would be the vector whose components are, let's see, 3 minus -1 is 4. Which of course makes sense because it represents how did I move to get from A to B. And if I was at -1 and I went to 3, then I've gone 4 units to the right. So of course it's positive 4. Then how did I get from 3 down to -2, you might ask? Well, I went down by 5. So obviously that component is -5. So you'll just slot that into this position here, 4, comma, -5. And you got to multiply that guy by t. But that's it. That's my vector equation. So now to write parametric equations, I just say, all right, the x coordinate equals the x coordinate, which is -1, plus the x component, which is 4, times t. There. X parametric equation. My y equation will be the y equals the y plus the y times t. That's it. So it's 3 minus 5t. And there you go. This orange set of parametric equations is going to be the equations that model the line that passes through AB. So they said do it 2 different ways, but I'm not even done doing it one way yet, honestly, because it turns out that really to fully write a set of parametric equations, you do kind of have to stipulate your parameter interval. Now, since we want the whole line, then we would want t to take on every possible value. So we're going to go ahead and stipulate that t is an element of the set of reals. It can be anything. Of course, you might just say negative infinity is less than t, which is less than infinity. You could give your interval as an inequality if you want to, or you can give it using set notation. I don't care. But they said they wanted us to do this a second way, and I say, all right, sure. Pretty sure I said that this point right here could be any point, so why don't we let it be b? If we let it be b, then these two sort of initial values would just be 3 and -2. I'd still add on the same direction vector, the plus 4t and the take away 5t. But this set of parametric equations would definitely return to me the exact same line, and I'll still just let t be anything it wants. Okay, great. So that's A, done. Now B says, hey, I actually only want line segment AB. And if you've been paying attention, then hopefully it's sort of easy to see that the way we parameterized our line, at least in example 1, this set, not this set, but in the first example, we let point A be our initial value. So we would get this point, -1, 3, when we let t be 0. So A is literally the point we get when t is 0. And then if you understand what the direction vector is doing, I explained it a bunch, then letting t be 1 literally means you're adding 1 AB vector to vector A, which would push you from A onto B. So literally point B is the point you get when t is 1. So if you wanted to modify these parametric equations so that they modeled only the line segment instead of the whole line, you just change this parameter interval. You'd say, hey, actually I need you just to start at 0 and go to 1 instead of going all the way from -infinity to infinity. By the way, yeah, include those values because I want a hard endpoints on my line segment instead of open sort. But there you go. That's literally it. If you just change the parameter interval, then this is now the answer to B. So a slightly more interesting question is, how would you change this if you wanted to get the same line segment out of line 2? Well, if you were paying attention, then the only thing we changed here was we sort of seeded our equation with point B instead of point A. So using the second set of equations, point B is actually associated with time 0. And I still use the same vector, the one that points from A toward B. So time 1 for this equation would push me from B to a point that's like AB units away down here. So if I wanted to go from B to A, I'd need to let t be -1, which seems to me to say that for this set of parametric equations, we'd go from -1 to 0 to get the same line segment. So the only thing we've really changed by reparameterizing the line is we've changed the t values associated with each individual point, but we haven't changed any of the points. We're getting the same line, just at different times. So that's A addressed. That's now B addressed for both of our different answers for A. So what do I do then to turn my parameterization of the line into the ray AB? And again, hopefully it's obvious. Again, for the original parameterization, this is now the parameter interval for part B. So the parameter interval for part C would probably just be some different interval of t's. We already, I think we're beating a dead horse talking about A being the point associated with time 0. If you want the ray that starts from A, you're probably going to let t start from time 0. Hope that's obvious. And if you want all the points on the right side of A, then we're back to just letting t go all the way to infinity, right? And then if I use this parameter interval, then I would get a ray that starts at point A and goes through point B. Now if I wanted to reparameterize and use the second set of equations that we wrote, then basically A is back to being associated with -1. You'd start there, but you'd still let t grow to anything greater than -1 would go all the way to infinity, and that would be my ray. Ooh, I'm running out of space. So I'll just give all this the old shrinkaroo. The old shrinkaroo. That's fine. Alright, and then for part B, D, I meant to say. For part D, we want to start with ray, we want to start on point B now, here, and we want to run that way. At least that's how people thought about it when I first mentioned this in class. I don't actually have to start at B and run to the left. I just want the part of the line that does that, but I can still, as t increases, I can come running down this line and then just stop at B. I don't have to actually change the direction in which the graph is plotted, because the direction that the graph is plotted is definitely sort of down and to the right. As t's increase, we're coming this way for sure. I don't have to change that. A lot of people thought they would have to change that to reverse the direction of the ray, but no, you don't. We're not asking you to change direction. We're just asking you to get a different part of the line. I want the left-hand side instead of the right-hand side. So all that means is letting t's come up from -infinity and stopping at the t value that's associated with B, which wasn't that 1? So if I just go from -infinity to 1, isn't that going to do the trick? The answer is yes. By the way, t can't equal -infinity. Let me get that out of there. Or why don't I just be true to myself? Let me just be true to myself and use the notation I like, which is to say t is an element of the set that goes from -infinity to 1. And then I can use the old soft bracket, hard bracket notation that I love so much. Alright, so this this parameterization here, it doesn't actually go from b to infinity. It goes from infinity down to b, and that's fine, because this ray is not supposed to be a directional thing. It just refers to which half of the line you want. We want the left-hand side, and we're getting the left-hand side, so everything is, as they say, hunky-dory. All right, I hope you understand that. If you do understand that, then why don't you jump ahead, jump way ahead to a little something I call the homework, where you're being asked to do that exact same thing a bazillion times. If you wanna, you could pause the video and you could do number 27. Then when you unpause the video, I'll have the answer right here waiting for you. Okay, click pause. So for 27, one way to parameterize the line that passes through those 2 points would be, I'm going to go ahead and do it the slow way again. You'd write the vector equation first. You go, okay, xy equals some vector that puts me on the line, which is literally any point on the line. I like 4 and 2. It doesn't have a negative in it. I'm going to choose that. 4, 2. Got it. Then I'm going to add to that the vector AB. But whatever. I'm going to go this way. I'm gonna go that way. So I guess I'm using vector BA. But I'm at 4. I'm going left 6. So negative 6. I'm at 2. I'm going that away. I'm growing by 3. Alright, so you know what I'm going to do just to be cheeky? I used to make my students do this, actually. If there was a common factor here, factor it out. Because doesn't parallel mean that vectors are scalar multiples? So instead of using this vector that's like all long and stuff, shorten it. Go negative 2, 1. That vector is guaranteed to be parallel to negative 6, 3, isn't it? It's just half as long. So that's kind of a better candidate, right? We should probably be using a unit vector, honestly, so that we know that we're always moving by a length of 1, length of 1, length of 1. It doesn't matter. This is my answer. I like it. Your answer may be different from mine, but this is what I'm doing. I'm going with this, and maybe that helps you understand it better. Maybe it doesn't. But my final answer, my parameterization would be what? 4. Take away 2t, and then 2 add on 1t. And hey, don't forget, your parameterization should really include 3 things. It should also include the interval of legal t values, which for right now would be all of them. So this thing right here for sure defines the line that passes through here and here. Just for, sake of argument, if this was A and B, let's answer those same questions. How would I change this if I wanted to only get line segment AB? And the answer is I wouldn't change anything about my parametric equations. I would just change my parameter interval. And be careful here because of what I did, and this might confuse you or it will actually help you understand better and more deeply. But T would be an element of, because my starting point is B, I'm certainly going to let t go to 0. Then because I used a vector, I actually used vector BA here, except super psych, I didn't. I chopped that in half, right? I chopped it into a third because I factored out a 3. So this vector is actually 1/3 of the vector that goes from B to A. So that means starting at 0 gives me B. But if you want to run all the way back to A, you better let t increase up to 3. So that's a pretty big difference from what I said previously. If we run back, I think I actually said 99 times out of 100 I was just going to use vector AB, right? And then not futz around with it. In this case, I couldn't futz around with it because my direction vector was 4, negative 5. 4 and 5 don't have a common factor to factor out. So I couldn't shorten that vector even if I wanted to. But in classic Mr. F fashion, I broke my promise pretty much immediately. And so I said 99 times out of 100. Let's just call this time 100 then, because I didn't actually use vector AB. I used 1/3 of vector BA, which then changes my parameter interval. I know I told you that you could pretty much always just go, okay, it just goes from 0 to 1. And that's true. if the vector that you used was vector AB, and if this is point A and this is point B, then you go from 0 to 1. But I wrote my equations a little bit differently. If you understand how what I did made the parameter interval be this, then you're smarter because of that. So congratulations. I hope I didn't confuse you though. All right, I'm gonna go back to work now and hope that you get that. Okay, moving on. So number two. Number two said, using this point, find a parameterization for a vertical line through that point. So they're giving us the point for -2. There it is. And they want us to model a vertical line. So as long as you understood what I said, this is kind of a piece of cake. I'm still trying to parameterize a line, so I would still start by writing a vector equation. And the only point they gave me is for -2, so I guess that's going to be my initial point. And then I know that the next thing I do is I write any vector that's parallel to the line, and I multiply it by t. Well, guess what? One example of a vector that's parallel to the line would just be the vertical unit vector. Remember everybody's buddy called J? J is the little vertical unit vector, like I and J. So literally anything, any vector that has 0 as its x component and then some y component would be fine. Unit vector seems to make the most sense here though. And then I'm now adding on a vector that just pushes me up. If t was negative, then this vector would push me down, 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 and I would get a vertical line. So my parameterization then would be x equals 4 plus 0 times t. That means there's just no t in the x equation. And then y equals -2 plus 1 t. And that's it. They do want the whole line, so we'll go ahead and stipulate that t can be whatever the hell it wants. T is an element of the reals. So that's part A. And then part B is doing that super predictable thing where it says, hey, instead of the line, just give me a ray. So it says, let that thing be our endpoint, but point down. So a couple ways to do that. I still want the same parameterization. I don't need to change my equations in any way. I just changed the t values that are allowed again. So we said that this point here is again going to be the point associated with a t that equals 0. Because I'm using the vector 0, 1, that vector pushes me up. So the top half would be associated with the positive t values. So I would only get the bottom half when I use negative t values. And I do want my ray to be pointing down. So that means we'll let t take on negative values and then come up to 0. And that change on my parameter interval will give me that actual answer. So let's say that I actually ordered you to parameterize this so that this point was the first point plotted, and then we plotted the ray pointing down, but that we did actually plot it so that it got plotted in this direction. Well, to do that, I would have to actually change the definition here. We'd still let x equal 4, but if you wanted to be plotting down, you'd have to change your vector equation. You'd have to change it so that the vector you're using is the vector that pushes you down. Then you could start at 0. How would that change my equation? It would make me go -2 take away t. You just change the sign of t here. So you go y equals -2 minus t, and then suddenly your t interval, you'd still start at 0, but you'd go ahead and use positive t values, and the vector will do the work of pushing you down. So if you really wanted, if you wanted your ray to get plotted in such a way that you started at the endpoint and went down, then you'd have to change the vector to make that happen. Because the initial parameterization that we used is always going to come up, 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 up from infinity and just stop at our endpoint, which is fine. But again, if there was a question on the quiz that specifically said you must plot the graph in a certain direction, then you might have to think a little more deeply. All right, number 3. We're 24 minutes on 2 problems. That's normal. God, if these videos were too long, you guys would say so, right? You guys appreciate that they're long, right? Because if you need to hear it, you can listen, and if you don't need to hear it, you just fast forward. Can someone say that to me? Like actually just grab me and say, they're too long, don't bother doing all this. Or grab me and say, this is good, I appreciate this level of depth. Okay, thank you. Thank you for doing that. All right, number 3. Find a parameterization for the upper half of a parabola having vertex -2, 0, and opening to the right. Okay, so suddenly all bets are off. We're not talking about vector equations anymore because vector equations, at least for us, the way we just talked about them, they can really only model a line, right? The general rule that I gave you only models a line. It's never going to curve and make a parabola or a circle. So no more vector equations. We're on our own. We're out in the wild again. But I'm pretty sure we know a hell of a lot about parabolas by now. We know how to parameterize them. We know certain parameterizations that always give us parabolas. We even know how to write rectangular equations for parabolas. We even know a new definition for a parabola as a conic section. Maybe we could make use of some of that. But we're saying -2, 0. That's this point over here. Blop. We only want the upper half of a parabola. Now it says a parabola. I know I harped on that in class, but the fact that it says a parabola means there's lots of parabolas, right? I could do the one that goes over 1 and up 1 and goes brrr. But if you wanted to model a parabola that was sort of wider, you could. If you wanted to model one that was skinnier, you could. Doesn't really matter. So that matters because, I was about to say, that probably a pretty good place for us to start here is with our conic section definition of a parabola, where our formula for a left opening parabola, or a right opening parabola, was x. It was x minus h equals 4p y minus k squared. And no, I never really got around to defining what p was. You know what? I'll do it right now. Here's what p is. For every parabola, there's a line that is perpendicular to the axis of symmetry of the parabola. And then there's a point. This point is called the focus of the parabola. This line is called, I'm serious, this is really what it's called, the directrix. No, you don't need to use that word. But that's what P is. P is just the distance from the vertex to the focus. So the way I've drawn it, that distance is 1. And notice that the distance to the directrix is also 1. Those distances will always be the same because the whole idea is every single point on the parabola is equidistant from the directrix and the focus. I'm not going to talk about that more. I'm just going to say that if you let P be 1, then that would give your parabola a certain width. If you let P be 2, then you'd be shifting your directrix over, you'd be shifting your focus over, and that would make your parabola get fatter. And that shouldn't make sense to you, but just trust me. If for whatever reason you let P be a quarter, you know, like because you wanted this whole term to just have no coefficient at all, which is what I think you should do, then that would pull the directrix way in tight, it would pull the focus way in tight, and that would actually make your parabola get quite skinny. Again, just believe me. But hey, all that's to say, does it matter if my parabola is fat or skinny? Or did they say any parabola will do as long as it has the right vertex? That is what they said, right? So all of that long-winded explanation was just to justify the fact that in my equation, x minus h equals 4p y minus k all squared. I am going to go ahead and just choose for p to be a quarter, and then I just have no coefficient here at all. And then I can just start slotting in these values. It says x minus 2, so that will be an x minus minus 2, which is x plus 2. And then k, very conveniently, is 0, so I just get y. Oh, you're telling me my equation was literally just this? That's pretty simple. You guys probably could have got there. I'm kind of pretending here, of course. It's sort of simple. A lot of you probably would have guessed that you just could have written an equation that looked a lot like this, but I think that background I don't know. To me, it was important. You guys should understand. You're supposed to at least go forward into calculus with some knowledge of conic sections, including parabolas, and parabolas we haven't talked about that much. So anyway, you have an equation. How do you turn this equation into parametrics? Well, one way to do it would be to just say, well, if these things are equal, then why don't I just let this thing equal t and let this thing equal t, because t equals t, right? You're kind of doing like a reverse substitution. Like you could start with the equation t equals t, and I know that's true. And then you can go, well, if x plus 2 equals t, then x plus 2 equals t. And then I have an x equation. And I can go, oh, and y squared equals t. And then, oops, there. Those are now parametric equations. I'm not sure I even need to clean them up. I think if you stopped here and had them both solved for t, that would probably count as parameterizing the thing. I wouldn't stop there. I would definitely subtract 2 from both sides and say that x equals t minus 2. And here I guess I would take the square root of both sides. And of course I would never ever forget that that's going to generate a plus or minus. And so there's my parameterization. Unless I'm overlooking something, which guess what? Of course I am. They said they wanted the upper half, right? But if I do plus or minus, then haven't I just opened the door for our parabola to take on positive y values and also negative y values? So I can think of a couple ways to correct for this. Could I just put a parameter interval on here that would cut away this bottom half? Actually, no, because this bottom half and the top half, they're being generated at the same time by positive t values. Like imagine if t was 4. You plug in 4, and you're literally getting positive 2 and negative 2. You're getting them at the same time. They're both generated by positive 4. What happens when you plug in negative 4? When you plug in negative 4, you get an imaginary output anyway. So there's actually a natural restriction on t that t really has to be bigger than 0 anyway, otherwise you're going to get imaginary outputs on y. So you could say that t can be anything. You could say that t is an element of all real numbers, but any negative input that you tried to use would just kind of fizzle out, and it wouldn't really yield a real value anyway. So we're kind of going 0 to infinity over here anyway. And with the plus or minus, I'm going to get the top and bottom half. So basically, like 80% of you who probably forgot the plus or minus anyway, you need to take the minus away. Actually, the only way to parameterize this thing correctly is to just, oops, I forgot that there should be a plus or minus, and make it plus only. And then the parameter interval could just go from 0 to infinity. If you said all reals, I wouldn't mark you down, because that's fine. This would actually still yield the same graph. You'd just be giving me a bunch of t's that don't actually work. But it's not really wrong to like say they're allowed and then just have them fail when they get plugged in. It would be nice if you knew that this was all I actually needed. That would actually be great if you knew that this was all we actually needed. But there you go. We did it. We parameterized the thing. I want to say more about this, but I think I'll screw it up if I do. Yeah, I don't know. I'm just not going to say it. It seems to me like I should certainly be able to have a parameterization here where y just equals some linear equation of t and x equals some quadratic form of t, a t squared. But it doesn't work to just square both things. Like that doesn't really work. So I'm just going to shut up about it, I think, and I'm just going to let you do it. I said a bazillion times that parameterizations are non-unique, so you might have come up with a parameterization that's different from mine that works better. And if you did find one where t, like down here, if this was just plain old t and the x was something else, that might be a more elegant parameterization. But mine's fine, so I'm moving on. Alright, find a parameterization for the hyperbola whose rectangular equation is that thing. First of all, I would say, whose rectangular equation is. I'm sure they meant for the hyperbola, comma, one of whose, because these rectangular equations we're learning really aren't unique either. And I would say when it comes to hyperbolas, we like to see these bad boys equal to 1, don't we? So shouldn't we see divided by 4, and then divide this by 4 so it equals 1? This should be the version of the rectangular equation that you guys are more familiar with. That's the version that might allow us to convert more readily into parametric form. I would like to think you guys can just convert like right away, but I don't know. Maybe you can't. Let's find out. X equals, Y equals. The middleman between the rectangular form and the parametric form, in my opinion, would be sketching the graph and kind of remembering the properties. For H and K, I see 0 and 0, so this guy's centered at the origin. Both of my denominators are 4, meaning I go left 2, right 2, up 2, down 2. And instead of a reference rectangle, I'm just getting a reference square. And that square gives me my asymptotes when I go through the opposite vertices. And now the only thing left to decide is, do I open uppy downy or do I open lefty righty? And again, because the y term comes first, I'm going to open uppy downy. So that means I have a vertex here and I go up, 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 up. And I have a vertex down here and I go down, 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 and down, down, down. So there's my sketch. All right, the fact that y comes first, well, I guess I didn't even need to draw the graph really. I should have done this right away. The fact that y comes first, in my trig identity, doesn't it have to be the secant squared, take away the tan squared in that order? So that seems to indicate that my y equation must be the one that includes secant. My x equation must be the one that includes tan, otherwise I won't open in the right direction. These 4s we're dividing by tell me that my distances here are 2, and those are the coefficients on the trig functions, right? And then it's 2 tan t, 2 secant t, and the center gives you the h and k, which is what we're adding on to the end here. So it's plus 0, plus 0. I'm done. That is a parameterization of a hyperbola. Are there other ways to parameterize this? Sure. Does this way work though? Yes. Should I indicate an interval of t's? Yes, I should. Can I just let t be whatever the hell it wants because they didn't stipulate anything? Yeah, I can. What if they had said they only want the top half? God, how deep into this do I go? I wish this was live, and you guys could just tell me if you wanted me to keep talking. Just gonna do it, and if you don't like it, then fast forward 5 minutes or so. What if they had said to you that they only wanted the top branch of the rectangular equation, or they only wanted the top branch of the hyperbola defined by this rectangular equation? Well, I guess we got to do that thing. If I had asked you to graph this, which might I ask you to graph it on the quiz anyway? Yeah, I might. And shouldn't you be plotting which point is associated with time 0? And shouldn't you be plotting or indicating the direction of growth anyway? So it sounds like we're doing that. So t, x, y. You can just be plugging in 0 and evaluating. I don't much like evaluating things algebraically. If you ask me what tangent of 0 is, I don't know. I don't have it memorized. I literally remember what the tangent of 0 is because I remember what the graph of tangent looks like. Graph of tangent is the one that goes like this, right? So tangent of 0 is 0 because we go through the origin. So when t is 0, our x is 0 because it's defined by the tangent function. Secant, what's secant of 0? Hell if I know. But I remember that secant is the guy that's a cosine function flipped over. So here's my cosine function, does one of these. So my secant function must do one of these. We asymptote, we asymptote, we. So secant of 0 is 1, but 1 times 2 is 2. So my starting point is 0, 2. Who would have guessed? Whoever would have guessed. It's that point right there. So t equals 0. Now the question is, in which way do we grow? From here, are we growing out to the right or are we growing out to the left? And the answer, of course, is, well, just look at your x equation. these x's are defined by a tangent function. Tangent functions grow, so I guess my x's are increasing. So I would expect this hyperbola to immediately be growing along this branch. Now the strange thing is, you're not gonna get this other branch until last. The way this hyperbola actually plots is you go up this branch, then you come up this branch, then you go running down this branch, and only then do you finally come crawling down this branch. So how the heck do I find a parameterization for that? Well, I'd like to think you understand that it's kind of the secant function that's causing all this to happen, because we're getting positive y values, then we're getting negative y values that increase, then we're getting negative y values that decrease. That's literally this branch. Look, we're getting negative y values that increase. So if I could like divide this up or something, but there's the asymptote, there's this local max, there's this asymptote, and there's 1, 2, 3, 4 distinct regions of the first period of secant, right? You've got your positive increasing y's. That's this branch over here. I feel like what I'm saying is pretty good. I should maybe make this neater and color code it. You know what? Let me hit pause and see about doing that real fast. Okay, I'm back. So here's some graphs. Maybe this will make sense. But here's my idea. It's important that we remember that yellow dot that I just placed there, that's times 0. And over here, this is 0 on the graph of secant. Notice that 2 secant is giving 2, so we get a y value of 2. And then look at what this branch is doing. The y's are increasing. So as the x's are going to the right, we see the y's are increasing. Watch now as I switch to orange. The next branch is we pick up here, and we're coming up from negative infinity. That would be this branch here, coming up to negative infinity and going here. Then watch as I switch to green. Those same y values start to go back down to infinity now. That would be us running down this branch now, all the way to infinity. And then watch as I switch to blue. After this green, we now start coming down from infinity to here. And that's us coming down along this branch. Blop. So there's your sort of color-coded guide to how this graph plots itself. I know we've been saying, okay, plot times 0, okay, times 0, and then tell me which direction we go. We go that way. That's not really sufficient for a hyperbola, is it? Like, we should really understand now that as t increases, by the way, t only has to increase from where? 0 out to 360. The period of secant is just 0 to 360. That means this whole graph gets plotted just between 0 and 360. Then the whole cycle just starts again, right? If I kept going after the blue, I'd just be getting all this yellow crap again. And I'd just be tracing that same branch of the hyperbola. If I kept going after the yellow, I'd just be getting this orange crap again. And I'd come up this branch. And if I let that go, I'd get the green again. And it just repeats. But so it's sort of important to understand, I guess, that yes, we start here at this vertex, and then we trace the yellow, then we come up the orange, down the green, then down the blue. Hey, with all that in mind, if I actually told you then to limit the t values here so that you only got this top half, how would you do it? Well, I think I just told you. Right here this is 90. When this thing runs off to infinity, that's analogous to a t value of 90 degrees. If you wanted this half over here, well, I think I just told you, if this whole thing is cyclical, then right here, that's the blue bit again. So couldn't we just let the t values go from negative 90 to 90? And I would get only the top half? Hey, we did it. And by the way, these, you don't have to let these be inclusive, because if you included it, you'd just be including the asymptotes, which don't get plotted as part of the hyperbola. But if you did include them, you'd be including the asymptotes, which don't get plotted as part of the... It wouldn't really be wrong if you included them or didn't include them, but that was a lot of work for a problem that nobody really asked, but maybe that's foreshadowing to a question that somebody is going to ask. So if you wanted to write a parameterization for that hyperbola, but only getting the top half, maybe the easiest way to do it is to just stipulate that t can only run between -90 and 90. That would generate the top half only. Interesting. I think that's interesting. You could tap me on the shoulder in class and say, hey, Mr. F, that aside that you put so much time into and included color-coded graphs so that I would better understand how to put limitations on my parameter interval to get a certain section of the graph, that was interesting to me. You could tell me that, and I would smile at you. And that would be all. All right, that's 4. We did 4. Great, moving on. 5. Oh, weird. It's a parameterization where you only want the left half of a circle. It's almost like if we were going to do a hyperbola but only want the top half. It's actually exactly like that, right? So if you understand the hyperbola one, this is like your black belt in parameter intervals. This is like you're going back in time and fighting a white belt. White belt's the first belt. That's the easiest belt. So if you're a black belt, fighting a white belt would be really easy. Got it? You get what I'm saying? All right, so this question about a circle should be a piece of cake. I'm sure you all know that every single time we saw parameterizations where x and y involved sine and cosine, we got a circle, right? Haha, tricked ya. Actually, when we had sine and cosine, we got circles sometimes. We got ellipses sometimes. And I guess that's it. Technically, we could get other stuff too, but usually with these, we got circles. We got circles as long as the coefficients were the same, remember? They're asking us for a radius of 2. I'd like to think that after everything I've said in this video, you get that these coefficients want to be 2. So if I want to be a circle, I'll let both of these things be 2. If I had described you some ellipse that had a major axis of length, let's say 10, well, half of 10 is 5. You would know that you would want the coefficient of x to be 5. That's sort of the x distance. And if I told you that the minor axis was of length, I don't know, 4, then this would be 2n2. So you'd want this guy to have a coefficient of 2. If those coefficients were different, then suddenly you're getting an ellipse instead of a circle. I think that's probably pretty obvious to everyone by now. But we're a circle, so it should be 2 and 2. Now, the other thing that's a little bit weird here is we did say it didn't really matter if we parameterized this where x was sine or if we parameterized where x was cosine. Both of these parameterizations yield circles. We saw that. We did a whole activity about it. Now I am ignoring the center for the moment. Let's not. Let's go ahead and just put it in there. If you want to be centered at -1, then take 1 away from the x's. That'll pull you left. If you want to be centered at 2, then add 2 to the y's. That'll push you up. There's my parameterization. Now if I switch the functions, I don't switch what's what. The -1 is still attached to the x. You still want to take 1 away from x to go left, and you still want to add 2 to y to go up. So both of these sets of parametric equations parameterize the circle that is centered at -1, 2 with a radius of 2. So at the moment, these are both acceptable answers. They said we only wanted the left half though. So how would I make that happen for both of these parameterizations? Let's find out. I bet it has something to, oh my lord. I bet it has something to do with thinking about your starting point and your direction of rotation. So -1, 2 would put me here. Then I'd get a point over here, I'd get a point on the x-axis, point there, and a point there, and there's my circle. Alright, based on this parameterization, what do you get when t is 0? Well, at time 0, sine is on its midline giving 0. 2 times 0 is 0, take away 1 is -1. And let's see, cosine is at its max at 0, giving 1. 2 times 1 is 2, plus 2 is 4. So you're getting the point -1, 4. You're at the top of the circle. And if I'm at the top of the circle, there's nowhere to go but down, so forget the y. Think about x. Am I rotating clockwise or counterclockwise? Well, sine, again, is an increasing function. So that means if this is time 0, then as the x's first, or as the time first starts to grow, the x's start to grow. So I must be going right and down. We're definitely getting clockwise rotation here. So I don't want that half. So what would my parameter interval be? I want the other half. So one way to do this would be just don't start at 0. Let this thing rotate halfway around, and don't start until 180, and don't stop till 360. That would work. That would actually start plotting here and keep coming around like this, and it would give you the left-hand side. So this is one acceptable answer. Obviously, I could also just start here as -180 and let it come around to 0. If you were thinking that one of these ends had to be 0, then that's how you do it. You just let t start at -180 and come to 0. -180 would be this point here and would rotate around until we got back to 0, and that would give me the left-hand side. So that's what would work here. Now what if we use this other parameterization though, where x was associated with cosine? We would still get the same circle. We'd be here and here and here and here and here, getting the exact same circle. But by the way we've parameterized, our starting point is a completely different point, because this time when time is 0, cosine's starting at its max at 1. 2 times 1 is 2. Take away 1 is 1. We're starting at 1, which can only be this point. I don't really need to figure out why. It's got to be 2. But just to check, sine of 0 is 0, times 0, plus 2. Yep, 1, 2. So we're starting here. And where are we going? Well, we're definitely going left from there, but are we going up or down? Sounds like we should look at our y equation. Again, we should be expecting increasing y values from the sine equation. So you should be expecting to start here and go up. Alright, so again, if you only want the left-hand side, this side, and this is time 0, then you better start your clock at time 90 and stop your clock at time 270. And you would expect to get the left-hand side of the circle by starting at the top and rotating around counterclockwise. So that's it. There's a pretty in-depth discussion about how to use parameter intervals to only get a certain piece of a graph. I'm happy with it. Video is now 53 minutes long. I know how you guys like to complain about 53-minute videos. So let's make it longer. Let's try to get over an hour. Alright, part 6 says find a parameterization for a circle with a center here and a radius there that begins on the x-axis, rotates clockwise. Alright, piece of cake. Easy peasy. This will be the last one for sure. Alright, I think we just said that if you want a circle, you're just going to let x be some function of sine or cosine. Let y be some function of cosine or sine. But this one specifically says it wants to start on the x-axis and rotate clockwise. So let's sketch that out. See what the heck they mean. We want to start at 3, 0. We want to have a radius of 2. So that puts me here, here, up to here, down to here. Okay, so when they say starts on the x-axis, they're still not exactly, hemming you in to one way or the other. We could still start on either of those orange points. So let's see. As far as, this is going to be confusing, but as far as y values go, it seems like that's putting me on the midline. Who starts on the midline? Oh, sine. So I guess y would have to be a sine equation if I wanted to start on the x-axis. We'll do sine t. If my radius is 2, pretty sure I need a coefficient of 2. If my center is at 0, then I'm pretty sure I should not add anything here. Now the other way to think about it is, this same point on the x-axis, x-wise, those things are starting at maxes. Those x's are cosine functions for sure, because that point is either a max or a min. So if I was starting here, I'm starting at my maximum possible x value. If I was starting here, I'm starting at my minimum. Either way, this for sure has to be the cosine function. So that's cosine t. It needs a coefficient of 2, and somebody has to add 3 to it. There. I am now quite confident that this parameterization will start me at this point. That point will be associated with time 0. That again is because cosine of 0 starts at its max, which is 1, times 2 is 2, plus 3 is 5. I'm definitely here. And sine starts on its midline at 0. 2 times 0 is 0. So I'm at 5, 0, like I want to be. Now, they did say we had to rotate clockwise, and this is where things get a little weird, because I want to go down. But I've modeled y with a sine equation, right? Pretty sure sine equations start at the middle and come up. So as written, these parametric equations are going to start where I want them to start, but they're going to rotate counterclockwise. So how do I make it go clockwise? Well, I just said, we go clockwise because this function increases out of the gate, right? How can I make it decrease out of the gate? What could I possibly do to a sine equation to make... Oh, right. Just reflect it over the x-axis. Don't you do that by just making the coefficient negative? Leading coefficient negative. Oh, I'm done. I did it. I've parameterized a circle with these very strict requirements. I definitely am starting at exactly the right spot, and I'm rotating in the right direction. Got it? I hope you do. Okay, I'm back, just to illustrate this better for people who want to see it. Again, you don't even know that I left because I hit pause without saying anything. But I'm back, and look, I brought a demonstration. So, look, it's a circle. Its equations are the parametric equations we said that they'd have to be. Can I make this bigger? Sure can. Alright, that's good, I guess. Alright, what did I say? I said that if we left everything here positive, then as t increases, the dot goes up first, and it comes around, around, around. And if I let t go from 0 to 360, it just makes one trip around the circle. I then said that all I had to do is change this to a negative. Boop. Now when I hit negative, you don't see the graph change. It's the same graph. Even when I hit negative here, our little point doesn't move. But watch what happens now as t increases. We're now tracing a sine function whose y values decrease right away. So this point's going to come down. Now I didn't change x, right? These x values are decreasing still because we started at a max. We got to come down. So we're still going left in the x direction, but we're now going down in the y direction. I mean, picture's worth 1,000 words. Watch. Oh, yep, yeah, it happened. I go the other way now. So that's the only change, right? The only change was that minus sign on my y equation. If I take it away, then my point goes back to rotating up first. Look, see? Up it goes. But if you put the minus sign back in, boop, then you're reflecting your sine function. Your y values now decrease out of the gate, and down we go instead. So there. That's that question. You know how I always say, hope that helped? I'm not going to say it this time. I know that helped. If you bothered listening, then that helped. So, good for you. Alright, I'm done. I'm done with that lesson now. We can put that baby to bed. All at 1:45. So, see you tomorrow. Bye.